The broadcast is now starting. All attendees are in listen-only mode.
Okay, good morning. Hopefully everyone can hear me okay. So, thank you all for attending our webinar today. If you experience any difficulties in hearing the broadcast, please see the settings shown on the slide and we'll try to assist you if we can. We're on quite a tight timeline this morning, so if you do have any questions, please submit them through the questions pane in the GoToWebinar questions box. We have an engineer online that will also answer questions throughout the session, but if we do not have time to answer your question, we'll get back to you following the event. I'd like to make you aware that this webinar will be recorded and available for viewing later through the website. If you have any questions following the event, please feel free to email them through. Details will be posted for this at the end of the webinar. Okay, so let's begin. Welcome along to the first of our two webinars today for an introduction to SCIA Engineer Part 1, focused on the creation of concrete structures. My name is Chris Daly, I'm the account manager for the South of the UK. I'm relatively new to SCIA, but have been working within design, engineering and software for over 15 years. Our engineer for the introduction to concrete structures is Thomas Pyle, whom I will be handing over to shortly. Thomas has been working with SCIA for over 5 years and he is our product manager for concrete. The agenda for this morning's session will be as follows. We'll start with a brief introduction to SCIA with some background information, its development and where it is today. I shall then hand you over to my colleague Thomas for the main technical presentation. We shall aim to finish at 10:45, and as mentioned, if any questions are outstanding, we'll be around at the end to try and answer those, but also we can contact you following the event otherwise. So a little bit about SCIA. SCIA has been part of the NEMETSCHEK group since 2006, for those that don't know. NEMETSCHEK are a multinational organisation that originated from Munich in Germany and have been in business for over 50 years. The NEMETSCHEK group is driving the digitalisation of the building industry. They specialise in providing the best AEC software solutions for architects, engineers, construction companies and facility managers. They have a commitment to innovation and providing flexible and open BIM solutions. As part of the group, SCIA are committed to providing the best and most innovative products for the structural engineering industry. We're solely focused on this since it is the only industry we serve. Founded in 1974 in Belgium, SCIA is now a global and diverse company that has employees from over 15 nationalities. We have over 4,000 customers in 50 countries. There is always a focus on investment back into the product for continuous improvement with each yearly release. The improvements with the software are based on customer enhancement requests, ensuring you get the capabilities and productivity more efficient with your projects. SCIA's headquarters are located in Hasselt, Belgium. We have offices throughout Europe where usage is most popular, although SCIA is present worldwide. Many of our offices now supply directly to our customers, although our team includes a selection of resellers throughout the world also. Our team has recently grown in size to ensure we can provide the right level of support for our customers moving forwards. We have offices in Czech Republic, France, Netherlands, Slovakia, Switzerland, UK, and more recently Germany has become direct. Our resellers include locations in the US, South America and Asia, as shown on the map. SCIA is dedicated to the continuous improvement and innovation of its products. Some of the innovations over the last 10 years have included a move towards more accessibility with an open API and integrated workflows with proprietary software. It has developed full integration of Eurocodes, IFC certification, as well as advancements with steel fibre reinforced concrete. More recently, there are some great new enhancements to be released as part of SCIA 21, which will be showcased in April-May time. 2020 also saw the introduction of a new product called the AutoConverter. So, a very brief introduction. The SCIA AutoConverter offers users a unique workflow that enables a more efficient way for the structural engineer to become part of the open BIM process. Working with all types of modelling and analysis software, it bridges the gap between the two and provides a conversion process that is proven to save engineers hours of time through the reduced editing and remodelling of geometry. This means the engineer has full control over the analysis model. The modeler can focus on the structural model and doesn't need to give attention to the analysis model. There's huge flexibility in creation of the analysis model, since different analysis models can be created from one structural model. This is a fully open BIM solution. There's more information available for this on the SCIA website. So that was a very brief introduction to SCIA AutoConverter. As mentioned, if you would like to know more about that, I'd suggest just going on the website or getting in touch. Moving on, we'll be focused today on SCIA Engineer for our technical demonstration. So what is SCIA Engineer? SCIA Engineer completes structural analysis and design software, enabling structural engineers to create their best structural designs in the quickest, accurate, and most efficient way every time, regardless of the structure. It means you can invest in just one tool to handle all your projects. It supports all commonly used construction material, all types of structures, and many different analysis types. It provides the freedom to model anything, effectively combine various materials for any geometry, simple or complex, with a powerful user interface and CAD-like modeling to provide the flexibility to address any project. The advanced analysis provides accurate results, and you can form the type of analysis that corresponds to the complexity of the project, whether this might be linear, non-linear, stability, dynamic, and more. Automated mesh refinement guarantees accurate results every time. To elaborate further, SCIA facilitates any type of structure. SCIA customers design multi-storey car park, residential buildings, shopping malls, industrial plants, warehouses, bridges, and more. Any material cross-section, cross-defined materials, code-defined materials such as steel, concrete, timber, aluminium, as well as editable properties for user-defined materials are all possible. Any geometry can be modelled, including linear members, beams, columns, surfaces, slabs, walls, shells, connections, intersections, supports, and hinges. Membranes and cables can be analysed. For loading conditions, there are many possibilities, including free forces, thermal loads, load panels, soil pressure, snow, wind generators, and more. For advanced calculations, finite element mesh is generated in the background and features automatic refinement for selected load cases. There is optional manual refinement along a point or along a line. Other analysis studies include static linear analysis, local nonlinearity, and geometrical non-linearity for initial imperfection and second and third order calculation. Material non-linearity for masonry and plain concrete is possible, as is plastic analysis for non-linear material behaviour for 2D members. This can be combined with other non-linearities in SCIA Engineer. For stability, linear and non-linear analysis can be applied, and users can input for the number of buckling modes to be calculated. Non-linear stability and dynamic analysis is possible for natural vibration, non-uniform damping, harmonic vibration, seismic analysis, and more. Construction stages can be calculated with linear and non-linear analysis for stage geometry and stage sections. Soil structural interaction is possible with geologic profiles, soil stiffness based on settlement, and multi-constant soil model. Finally, there is extensive code coverage with the Eurocodes and national annexes for 23 countries. SCIA Engineer includes integrated cutting-edge technologies such as parallel processing, automatic mesh generation, as well as innovative optimization and reporting tools. There is a logical user interface with intuitive workflow and powerful tools such as load generators for wind, load panels, and mobile loads. With parametric design, the creation of templates, typical structures, user blocks, and predefined shapes all mean time spent on repetitive tasks and iterations of design are dramatically cut. You can create bespoke reports and automatically update them, making your work in SCIA Engineer faster and more efficient. After you've created your final report, significant changes may still occur. With SCIA Engineer, you can simply hit the refresh button to have everything updated and ready to print. To support our customers, we have a dedicated support team of qualified engineers to help every step of the way. Quick start learning videos, tutorials with sample projects, webinars, and a comprehensive learning zone are all readily available through the website. Have full control over all your project design data and design your structure with confidence, thanks to comprehensive codes and detailed outputs. Within SCIA, maintaining control over large models is straightforward, with intuitive and simple navigation, plus filtering tools for layers, multiple selection options, and table inputs. This enables clear 3D visualization of the model at all stages and enables review of elements individually or in the context of a group. Clear, detailed output of code checks are available with all intermediate steps. This includes the formulas used and applied code clauses listed in the report available for anyone to review. The final report can be customized to the required level of detail, for a single table summary with a brief overview to a complete in-depth report. SCIA Engineer provides the most comprehensive implementation of the Eurocodes, including national annexes. In addition, it includes input from the latest research publications. This quality-driven approach is applied to all supporting materials, including steel fibre reinforced concrete, cold-formed steel, and steel concrete composite floors. For customization and always up-to-date documentation, integration tools like Picture Gallery, Paperspace, and the customizable engineering report help you to present the project to other stakeholders. These tools are invaluable when the project needs to be inspected closely throughout its various stages. Interoperability with BIM software across the construction is a priority for the future, although SCIA has many of the tools available today. This provides the possibility to collaborate more easily with third parties. You can reuse existing data or rework models at a later date to save time and cost. SCIA Engineer plugs it easily into any workflow, reducing manual tasks and modifications, whilst making a project more efficient. The architect, engineer, and other project stakeholders can all work collaboratively on a project with a specific set of tools and digital models. The links to proprietary software, such as Revit and Tekla structures, optimizes your workflow, utilizing the strongest points of individual software and maximizing your efficiency. The links are designed to support all types of structures, materials, and geometries, and you can see revisions made by the other parties for easy tracking and transparency. Data exchange with Rhino and Grasshopper using the XML format or third-party plugins with SCIA Engineer enables you to work effectively with designers creating organic geometries also. Here is a selection of our customer base worldwide. Lots of references and case studies are available to view via the SCIA website. Our user contest, also featured in the corner, features submissions of projects from previous years, and I highly recommend visiting the website to discover this. It's listed under the Our Customers tab. So, to summarize, SCIA Engineer is a flexible all-in-one tool that enables you to optimize at any stage of your project. With a logical and intuitive interface, it's easy to navigate, and with powerful modeling analysis, enables you to build your best design. An expansive and customizable material library means no project is off limits. Finally, it has the powerful report generation tool to create the information you want to generate, with an automatic update to ensure you're always viewing the latest report. Thank you all for listening. I appreciate there's quite a lot to take in, but obviously if you have any questions, do let us know. I'll now hand you over to Thomas to begin with the technical presentation.
Good morning, ladies and gentlemen, also from my side. I'm glad to be here because I'm newly product owner for concrete functionality in SCIA Engineer, so I'm very enthusiastic to get your feedback. Also together with me is Radim Matela, who is moderator for the questions. So big thanks to him to be there. And about the content, the technical presentation is mainly for those of you who are not so familiar about SCIA Engineer and the functionality. So I will go from the very beginning to start modeling, then do some analysis and concrete reinforcement design. And through the presentation, I will build up the report so you can see also this part of the functionality. Okay, to do that, I will start from the scratch so you can see just a predefined line grid. Just quickly show the project data dialog, which is the first point where you will start the project definition. So I have specific materials for concrete and for the reinforcement. I select national code for actually Eurocode and national annex for British. From the functionality, nothing special today, and in actions I would like to just highlight I will use the automatic generation of code combinations. So I can start modeling. Before that, actually I will just check if I have visible line grid and tracking or snapping to the endpoints. I go to the structure service and I can start modeling. So first plates, I will define plate with thickness 200 and I will select the layer slabs where all the slabs will be gathered, and I will quickly use the line grid to define the geometry of first slab. I will continue with the second slab. And also I will finalize the slab creation. Here I will create circle boundary. And actually we have defined the slab's geometry. Okay. Now I will continue, for instance, with the openings. First, I will define the openings which will shape the boundary of the slab more. So let's cut out this part of the first slab. I will do the same for the second slab. And that's it. And basically, I will also create real opening. So I will select first this slab. And now I will specialize to create a circle opening, and you can see that the opening is now just on the master slab which I selected, so I can repeat the same stuff also for the second slab adjacent. Sorry, once more, because I need the circle, so I will use toolbar and we have it. Okay. So I have slabs with opening and a little bit reshape the slab by opening. Now what I can do is continue with definition of columns. So again, I can select now the cross-section for column. For edge columns, I will use this type of cross-section. The alignment will be, or insertion point will be the top, and I will select layer columns. And I can quickly again define the columns using my line grid. Here I will put the column as well, and we have quick definition of the columns, and I will do the same also for the inner columns with different cross-section. So I will put the columns here. Okay, now what I can do quickly, apply also the support for the columns. So in the model data, I can select support in node. It will be hinged, and quickly I will apply the support for columns. Okay, and I can continue with the final part from the modeling so far. And this is definition of the wall. Again, just be careful about proper layer. Insertion point is again the top, and thickness is 200. So first I will define the walls by selecting the line. And for the last part, I will do it again by definition using the points. Okay, now I can activate the activity which is predefined. So here I have a viewpoint for walls. So let's just activate it. I have my walls isolated, and again I can apply binary conditions. Now line on to remember edge, again hinge support, and we have it. Okay, so now I can, for instance, generate the mesh. I will visualize it using the toolbar, structure mesh. And also what I will do is display the local coordination system for the mesh elements. You can see that my mesh elements now follow the coordination system of the slab. What I can do actually is change the system from the standard to, for instance, definition by the point. So I will select the insertion point. You can see the coordination system has changed. And if I regenerate the mesh, you can see that now I have coordination system of mesh elements different from the coordination system of the slab. So for instance, by that, you can design the radial reinforcement later on, okay? So what's important that the coordination system of the mesh elements is the key for displaying the results and also for the designing of the reinforcement. So be aware of that. But for today's presentation, I will use the standard definition, but you can see that my column grid will probably or will lead to the principal moments in these directions, and I can see that my direction of the coordination system of the slab is different. So I will just rotate the coordination system to have the axis X and Y in same way in principle like the principal moments, okay? So I will just rotate the coordination system. Now everything is ready, so I can quickly calculate the results. First for the self-weight, which is automatically generated. So what I will do just here in advanced concrete setting, advanced solver settings, I will change the bending theory to Kirchhoff because we have thin plate. And basically that's it. Now I'm calculating the load case for self-weight. And I can start checking if my model is okay from the perspective of modeling. So for instance, I can go to the main menu, go to the results and check first the deformation, 3D displacements. I can show it, for instance, for the wireframe. And from the modeling point of view and deformation, it looks everything is okay. But what's obvious that probably here I will have problem with deformation later on, so we will touch it later by rips. I can check also the reactions. So again, for the self weight, I can select, for instance, a reaction for each support in direction of Z axis, and I can see also from the point of view of reaction forces, it's okay. I can scale it more, the results. And also I can display, for instance, the resultant. And in this resultant, I will store it in the table results. And I can compare it, for instance, with bill of material. If I display the bill of material, I can compare the total mass of the structure with the reaction. So by that, I have another control if everything is properly set up from the material point of view. Okay, I can also quickly check the internal forces for self-weight. So I will display, for instance, moments, but only on slabs. So I activate the layer with all my slabs. I will draw the moments in X direction, and I will show very important stuff which is related to the local coordination system. So let me just isolate now this wall and this slab. Sorry. So I will do it once more by this button, and I will create the section for presentation, the results, and I will actually display the internal forces on this section just, okay. And if I display the results and make it a little bit higher or bigger, sorry, you can see that now I have different value for the slab and different value for the wall. And I'm using in nodes average on macro. Now I will use different option in nodes average. And there is statement that I should be really sure I want, but yes. And I display the results. You can see that now I have the value on the slab and on the wall the same. So the common line between the wall and slab is using for the averaging. So actually I'm using also the same averaged results. And it's quite dangerous because you can see that if my local coordination system is not same, so you can see in slabs we have X direction here, but in the wall this is this direction, so the results are not compatible. So be really aware that if local coordination system is not same, you should always use in nodes average on macro or in centers, which again I am doing the averaging or smoothing the results just in the center of the elements. Okay, so that's it. So now I can go and define the rest of the load. So I will again just activate my slabs and I will hide the local axis. And let's go to the service for first for the load case definitions. Here I have the predefined self-weight. So I will just insert another load case for permanent load. I will use also two load cases for variable load, and they will be long-term. And it's important that they will be also exclusive. So it means just only one from this load group, load case, will be in each combination, a linear combination. Okay. So I will define another one in the same load group and with same properties like duration. And the final load case will be the load case for the wind. You can see now I have to change the load group to another one. And it will be not exclusive, but doesn't matter in this case. But I will say it will be wind. Okay. So we have it. If we have load cases, we can also define the load itself. So first, the permanent load, I will use surface load with magnitude 1 kilonewton per square meter and quickly apply it. The same I will do with the full pattern of the variable load. I have it as well. For the load pattern number 2, I will define it by the free load, again with the same magnitude, but now I will define the load just on some part of the slab and for each slab. So just quickly define. Okay, here. Here and also here. So I have it. Doesn't matter if now it's overlapping because I can click on generate loads and you can see it's automatically aligned. So also the opening is properly considered, etc. So now I'm ready to do the calculation, but before that, just quickly about the combinations. You can see I have automatic combinations generated with all the content automatically added there. If, for instance, I would like to explore the content of the combination, I can do it by this option, or what I can do is explode the envelope combination to some linear combinations, and I can see that always I have in exploded combinations just single variable load case QK, so because it's in the exclusive load group. But now I can delete these combinations because I will use just the envelope. Now I will run the analysis, and from the analysis perspective, I will use the automatic mesh refinement with just high target error, but doesn't matter. For today's presentation, I just need a rough mesh to have the results quickly available. So I will calculate first. Okay, so I need one step more because I need for automatic mesh refinement also assign some load case for which it will be generated. So I will use just the self-weight, and now everything is okay. To do the mesh refinement first, there will be error 36%, which looks quite big value, but normal value is between 15 and 20%. But here, what I can explore is actually to visualize what is the optimal mesh for this structure. So you can see that it's okay to have quite rough mesh, and now I can generate the mesh by clicking on the on this button to generate the mesh, and I can also visualize the mesh again. So now you can see in the singular in the points of singularity, I have the mesh more fine than in the rest of the structure. Okay, so now I can run the calculation with this mesh for all the load cases, and I will have everything ready to start designing the structure. Okay, so first, how I can design the structure is use, for instance, the combination for Euler's ultimate limit state. I can display, for instance, the bending moments in X and Y directions, or I can use the elementary design magnitudes, which are actually the values based on wood armor method. And I need just to again display it not on the section, but on the surface. So I can explore the design moments for upper surface in X direction. Same for the Y direction. I can select also the bottom surface, and again Y direction as well. Okay, for instance, I can choose another approach. I can define some integration strip with, for instance, width of 1 meter. I can quickly define one strip for this direction, and the same I will do in opposite direction. Okay, and I can go this time to results for 1D. Select the same combination and select I want results on integration strip. I can select the moment and Y and refresh the results, and I can see the results on, let we call it substitute beam, which I can use for my hand calculation, for instance. Yeah. If I go back to the internal forces 2D and select, for instance, the section on 2D, I will quickly define now the section, sorry. Again, for one direction, the same I will do for opposite direction. And I now can go back to the internal forces. I will use results on section, refresh the results, and I can see, for instance, just bending moments in Y direction for the bottom surface, and for instance, for the upper surface. I can say I don't want just the global maximum, to just see what's the peak value and so on. Yeah. Okay. But today's topic is designing the concrete, so I can start exploring the concrete functionality. First, I will be designing the slabs. So first point which I should explore is go to the concrete setup and define the design defaults for the plate. So I can see that for required reinforcement, I will assume diameter 10, and I can see the direction of the reinforcement is 0 degree and 90 degrees. So actually it will copy the direction of the X and Y axis. Same for the bottom surface. What I can do also to quickly say I'm using the template of provided reinforcement. So the required reinforcement will be covered by some real provided bars, and I can explore what will be here. So actually I will use the same diameter 10 for the basic reinforcement with spacing 150, and this basic reinforcement is applied everywhere, doesn't matter if it's necessary or not. And for the spaces where I need additional reinforcement, it will be designed either diameter 10 or 16 with the same spacing based on the required reinforcement area. Okay, and basically that's it for now. So I can quickly just go to the reinforcement design, select to the reinforcement design, again select this time the result class, and this result class I will use ULS plus SLS, so it means all combinations for both ULS and serviceability limit state is there. I can use for the speed purpose the results just in centers, and for instance I select to display the required reinforcement in first direction on upper surface. To understand where actually this direction and surface is, I can go to the view parameter settings, to the concrete part, and visualize the direction for the design. So I can see that as it is, my reinforcement directions assumption follows the direction of the coordination system of the slabs. Okay. So now I will do the design for ultimate limit state, but also for the serviceability limit state, for crack width limitation and reinforcement stress limitation. So I will calculate the results, and we can explore more about the designed reinforcement. So automatically I can see what is the direction for this direction 1, upper surface. It's as expected, so I have reinforcement above the columns in one direction. I can select another direction to see the results also there. I can explore also the bottom surface in one direction and another direction. Okay, what I can check is actually also the contribution from the ultimate limit state and serviceability limit state. So for instance, I will select first the for instance, check if in direction 1 for bottom surface, I have some additional reinforcement necessary from the point of view of crack limits or reinforcement limitation. So that's it. I can go back, for instance, to display direction 1. And for instance, I will load the results about this to the so-called table results. I'm exploring the lower surface and direction 1 minus. So I can sort the values. I highlight where my extreme is. So actually it's this place. And I can, for instance, display also the report from the calculation. So I can check what is used for the point of load, what is actually from the point of view of ultimate limit state, the compression height in inner lever arm, force in concrete, in steel, etc. Also from the perspective of cracking, you can see that this spot, everything is okay to use reinforcement from ultimate limit state in serviceability limit state. So I do not need some additional reinforcement. Now I can check this place where is necessary some additional reinforcement for serviceability limit state. Again, I can choose, for instance, this place and explore what's going on in serviceability limit state perspective. I can see, okay, so here I have some cracks. So because of this cracking, I need some additional reinforcement to keep it within this limit. Okay. Now I can start playing with that little bit more. So I can go to the concrete setup and say, for instance, that from the code-based settings, I will say I need just the settings related to the plate. And I will use the, for instance, effective modules of concrete to cover the long-term effect. And what I can, for instance, do is also limit the crack for the bottom surface to value 0.1 millimeter. Okay. So I changed my design assumptions. So I need to recalculate the results. So let's quickly do that. And you will see that now the situation will be different because in some part of the slab, the serviceability limit state will be the key player. So you can see now I have different place where this case is the most important. So again, what I can do is, for instance, load the results and explore the situation here more. And we will see that now I'm using the crack limit, which is lower than before. And because of that, I need to increase the reinforcement. Okay. So now if I see the required reinforcement, it's increased, and now I can check my provided reinforcement as well. So what actually we are talking about is if my assumption about real bars is sufficient to cover the required reinforcement. So I can see that almost whole part of the slab is okay to use just diameter 10 and spacing 150. In some places I need diameter 10 and 150 as additional, and for some spots I even need something more. Okay, I can explore different direction. So it's same situation. I can check also the upper surface where I can see that for the direction 1 I have some insufficient reinforcement, and for the direction 2 as well. So it means that for this spot my provided reinforcement is less than the required reinforcement. So again I can read the results. Into the table results about the provided reinforcement, I can quickly highlight, sorry, I will highlight this one. So you can see we are here now because we have direction 2. I can double click again to explore the results, and you can see that required reinforcement is 240 almost, but my provided reinforcement is lower. Yeah? So I need to react on that, and what I can do is use another tool, which is actually averaging strip. So I will define the averaging strip just above the columns where I have problem. Okay, so I will apply the averaging strip and go to the design and just recalculate the design. What I need to ensure that I'm doing averaging of peak for the design. Okay, So again, just calculate the design to see if it helped or not. And we can move on. So it's not helped, but what I can do is to show you what's changed from the perspective of the for instance, now I will display just results on the section, and you can see that from the perspective, for instance, of required reinforcement, upper, you can see if I'm using averaging, I have this kind of results. Without averaging, I will recalculate it, and you will see that the distribution of the reinforcement will be different with higher singularity. Yeah. So in this case, averaging is not sufficient. So I would probably need to change the reinforcement to higher diameter, or yeah, a little bit play with the model to, for instance, change the averaging size, etc. Okay, nevertheless, what I can do is again display the results, for instance, about the required reinforcement for the lower surface, and I'm going to build up the engineering report. Yeah. So, for instance, what I can do is just send this live picture into the engineering report. I will just insert it. Same, what I can do is also send the table to engineering report. I'm going to the engineering report itself, and you can see that I have some content there. I will create the result picture generator to derive also the pictures for other directions, and I will just indent the picture and the table under this result picture generator. Yeah. I will call it, for instance, 2D reinforcement and design, doesn't matter now. And I, for instance, select, okay, I would like to display or generate the picture for the direction 1 and 2 for the bottom surface. And basically what I need just to do is I can define for which members. So I will select the slab 1, 2, and 3. And I will use the averaging, and everything can be as it is. And I can regenerate the content. So you will see that automatically will be defined the result table. Now in this case, it's the numerical output. We call it brief. And from the perspective of pictures, I can see direction 1 and also the reinforcement for the direction 2. Okay. What I can do more is, for instance, build up other content, like I quickly define the stuff related to the load cases, load groups, combinations, etc. So I will just move down my reinforcement. I will delete this part which I don't need now. And you can see I have list of load cases, load groups, combinations, nonlinear combination I don't need. And basically that's it. What I can also change is, for instance, I need not the brief output, but my standard output. I will just select the direction 2 minus, which is the most critical one, and I can just regenerate the selected. And instead of numerical output, I will have the standard output with some details about the calculation instead of this overview. Okay, so I can see plate S3 as the most important with the designed value of required reinforcement in this direction, 1000, almost 1500, and the same value I will find also in my graphical output. Okay, so I can quickly do also another stuff. I will go to the main menu. I will hide the mesh, and for instance I displayed some load, for instance for this load. I can send this picture to the engineering report again. Okay, I go to the engineering report. Here it is. I move up with this figure. I intended under the load case. And actually just a little bit play with the figure so I can define, yeah, I will say it will be 100. I can regenerate the load cases, and maybe what I will do is also define the list of the load cases, and I will do just figures without the self-weight. And now I'm ready to just regenerate this part, and you will again see that the pictures with the load will be automatically generated. So I can see the permanent load, the variable full load, and variable load with some loading pattern, and also the wind. Yeah? The wind is not visible here. I don't know why, but I will explore it later. Doesn't matter. So we can see I can quickly build up also this part. And for instance, what I can do is to say, okay, I need also load cases from the perspective of the table and list. So actually I have everything what I need. So for now, from the engineering point of view, it's okay. So everything looks great. So what I will do is go to the final check, and I will check, for instance, the deflection. And this will be the codependent deflection. So it means semi-nonlinear calculation. So quickly I will define just the inputs. So I will use as an input of reinforcement for this calculation my provided reinforcement. So you can see I haven't modeled the reinforcement at all yet. I will use for the design of this provided reinforcement the same result class as I used. And actually that's it. And I will display first the total deflection. Yeah. First, I need to also check what will be my limit for the deflection calculation. So my span is almost 700 meters. So I will calculate by my total deflection limit, and I will do the same also for my additional deflection limit in same way. Okay, and that's it. And I can run the calculation. So what's actually now done on background is that I will calculate first the reinforcement design, then based on the reinforcement design, I will calculate the crack states, if the section is cracked or not. And based on that, I will calculate the stiffnesses, and those stiffnesses are then used to calculate the deflections, but not just for this calculation for total deflection, but also for other states, for immediate deflection where only permanent loads are present, or for my creep combination to cover the long-term effect. Okay, so basically by this calculation, I'm covering the cracks, I'm covering the creep effect, and also from the version 21 we are covering the shrinkage as well. Yeah. Now you can see that I have the results for the characteristic combination. According to the code, I should choose the quasi-permanent, but now I will not recalculate it. But it's obvious I have here problem with the deflection, so I need to react on that, because if I check, for instance, the limitation or the unity check, I can see that for this part of the structure, I'm not okay. Yeah? Again, what I can do is display the preview from the calculation. In this case, it will be numerical preview, where I can see that for both total deflection and also additional deflection, I am above the limit. Okay, so I will quickly go back to the modeling, and I will apply the additional part of the structure, which will be the rip. So quickly define the rip. It means basically I'm defining the beam on some eccentricity, which afterwards will be changed to the rip in post-processing results to integrate the internal forces on the new cross-section, and also do the check on the new cross-section where the both parts, plate and beam on eccentricity, will be joined together. Okay, so from this perspective, I will just select the cross-section. I will not use the automatic definition of the width for internal forces and for check, because I want to have it under my control. So for the internal forces, I will integrate the forces from the slab in width of 1 meter, while for checks, I will use just this part of the cross-section without the part of the slab which is outside. Okay, so I can define the rip position. I have it, and I can just recalculate the analysis. First, I need to calculate the analysis again for the mesh refinement. So now I can generate again the finite mesh. I can check if everything is okay. Okay, so I have a better mesh now, and I can calculate final step where I can get the internal forces for this mesh. Okay, I have now everything ready to go back to the concrete. And first I can explore, for instance, the internal forces on the rip. I can, for now, hide the mesh again. And I can select, in this case, class ULS, and I can display the moment on the rip. You can see that first I will display the results without the rip option, and I can change the visualization to see all the local values. So you can see here, for instance, I am about 50 and here about 40. Now I will activate, and maybe first, or not first, but I'm also displaying the normal forces now. So you can see that I have almost 600. So it means if I have beam on eccentricity, because of this eccentricity, I have obviously the normal force, which is in tension. Okay, now if I activate the rip option, I can again display the bending moment. And now you can see that the value is higher, while for the normal force, the value decreased. Yeah, because actually what happened is that my original force is decreased on the beam of in beam on eccentricity by the forces from the slabs which are actually in compression. Yeah? What I can do related to the internal forces, I can, for instance, explore the components. For instance, I will display the torsion moment. I can see there is some small torsion moment present on the beams. I can see also the moment about weak axis, also some small values. And in design, I would like to not take into account. So I can go to the concrete setup. And for the designing of the rib reinforcement, I can actually do the same like for the plates. So first I can define my design assumptions about required reinforcement, diameter 16, some cover which is automatically calculated. And for the template, I'm using the rectangular cross-section. So I can select some of predefined templates and explore the template, where I can see I will use diameter 16 2 bars as a basic reinforcement. So again, doesn't matter what is loading, it's put everywhere. And for the places where it's not enough, I will use again diameter 16, but I will design more bars according to the necessity. Yeah, I can choose another strategy to just say I need 2 additional bars with different diameter, and I can have some opposite approach. Yeah? Okay, and for the case of rib, I will just quickly filter what's valid for the rib, and definitely I would like to use the reduction of the shear force and moment above the support, and I would like to neglect for this case also the force components which are not interesting for me actually. So I can apply my engineering approach. So I will neglect the torsion moment and also the moment about weak axis, because I believe it will be transferred by the slab. And also I will neglect the normal force because I want to recalculate it as an additional moment on the rib. So actually I will design just on the moment and not on the combination of normal force and moment. Okay, so that's it. So now if I again display the internal forces in way to compare, for instance, bending moment original and the design one, you can see that from the perspective of bending moment, here is visible the reduction, and here is visible the increase of the moment based on the recalculation of the normal force. While, for instance, if I compare the normal force, the design it, you can see I have 0 values because this normal force, original one, is transformed to the bending moments. Okay, so quickly what I can do is go to the reinforcement design now, select the result class. Now I have option only ultimate limit state because for 1D I am able to design just for the ultimate limit state now. I can select the first the required reinforcement area and run the design on the ribs. So we will see the results and we can explore it more. So we have it. Again, I can display the local extremes to see all the values. Again, what I can do is, for instance, load the results to the table, filter some peak point for instance, bottom reinforcement, display the details of the calculation to see again the forces and what's actually calculated. Okay, I can see also the provided reinforcement, which is covering my required reinforcement. So you can see I'm using 2 diameter 16, doesn't matter if it's necessary or not. and where it's necessary, I'm adding some additional bars. Okay. What I can also visualize is the comparison of the required and provided reinforcement to see the utilization. Actually, it also looks good. So I'm able now to do the final step to convert this reinforcement to real bars. Okay. So now I can see that very quickly I'm able to generate the real reinforcement bars with proper length and proper position on my members. And I can also do the overall check of this reinforcement for the same load. I will just switch off the detailing for now and just check if from the point of view of unity checks the reinforcement is okay or not, but it should be the case. Okay, and actually I have the RIPs designed from the perspective of the reinforcement. So what I can do is now go to the engineering report, and you can see that now my results about the reinforcement design are not valid because I changed actually the model, but I can just quickly regenerate the results and see what's the new state. Yeah, so I had the extreme 1500 square meters per meter. So let's check what will be the new extreme and if everything is okay or not. So if I switch to the SCIA Engineer, you can see that there is some calculation on the background. Now the results are refreshing. And I can see that new maximum is the lower value, which is expected. And also the distribution of the reinforcement is different because now my weak point is actually here and not here as was in the past. Yeah. Okay, so finally I can go to the code-dependent deflection and do the final proof. Now I will select the proper input for the deflection and just rerun this calculation. Now the deflection will be calculated including the RIPs, including the reinforcement from the RIPs. So everything is again gathered together to have the final state of the deformation. So we can see again the design 1D stiffness calculation, and using these stiffnesses we are able to calculate the long-term deflection. Okay, so we will just wait for the results as a final proof that our structure is okay or not. So I now can switch to the presentation and just wrap up what we've learned today. So we are able for 2D design the required reinforcement in terms of theoretical areas, square millimeters per meter for ULS and ULS plus SLS cases. We are able to cover the required reinforcement by provided by bars defined in the template. We can, what was not shown, consider also the user reinforcement, so the real 2D meshes which are applied on the 2D member. I will show it later. And we are able to use quickly the provided reinforcement in calculations like punching or deflection check. Yeah. So now you can see that from the unity check point of view, everything is okay. If I display the total deflection, we can see that now the limit deflection is 21 millimeters. which is okay. Okay. So 2 more things quickly I would like to show you. First, we are able to do the same stuff or same approach, for instance, for the punching. So I can quickly check also the punching with this kind of inputs. And the last thing which I will show you is the combination of provider reinforcement and the inputted user reinforcement. So you can optimize the distribution of the reinforcement manually, for instance, to get better output for the draftsman, because you are able to export the reinforcement, for instance, to DVG, DWG, or using the IFC in BIM workflow. Yeah. So we are almost done. In case of punching, for punching there is limitation now. It's now available for only for columns and not for the corner or end wall. And if I check the local values, I can see everything looks good. What I can do again, read the results into the table results and sort the value, for instance, for the maximum capacity from the concrete perspective. I can highlight which is my problematic place. I can see that if I activate the real geometry and refresh the results, I can see that probably I should rotate the columns to follow properly the geometry of the slab, etc. Yeah. Doesn't matter. The last point which I would like to show you is the combination of the required and provider reinforcement. So I will display, for instance, the provider reinforcement for the bottom surface, direction 1. Now I'm designing also the walls because I have not activated the activity. So sorry for that. It will take a little bit more time, but I have it. And let's say that we would like to cover this spot by some user-defined reinforcement. And also, for instance, this spot here. Actually, there is one trick to be able to display the results or apply the reinforcement with visualize the design results. So you have to go to the shortcut menu and define for the reinforcement 2D input some shortcut. And now I can just apply this shortcut, select the slab where I would like to apply my reinforcement. I will use this diameter 16 as additional bars. Yeah. There was cover, I remember it, 35 millimeters. And I will use the spacing again as was originally used. Okay, so everything is defined. And now I can define my geometry. Yeah. So for instance, I will use the rectangle possibility, and I can see, you can see I can define the reinforcement 2D meshes for more places than just one. Yeah? Okay, so I can confirm it, and I will just refresh the results for this slab. So actually my provider reinforcement I expect had changed, but you can see it's not the case because I forgot to activate consider user reinforcement option. Yeah? So once more, and in this case everything should be okay. Yeah? So you can see that I can optimize. If I would have better mesh, I'm able to really define the 2D meshes on actually real positions. Okay, so back to the presentation. Just to wrap up, Also for 1D design workflow, the same approach, required reinforcement, provided bars. I can use in case of 1D automatic conversion of provided bars to real applied bars, and I can use the checks on member or in section as I want. Yeah, so just really last thing which I will show is, for instance, approach of the section check. If I display, for instance, internal forces on my rib, I will select the design moments, and now I will select just this rib, and sorry, so I can see some extreme bending moment. I can activate the option section check, select this section where is the extreme, and display the tool where I can explore the reinforcement and the results as well. Yeah, so I can check the capacity diagram, for instance, in detail output. So also very nice approach how I can even optimize the cross section. So I can, for instance, define 5 bars. You can see it's not sufficient, but I can try to change it to diameter 20. And okay, so it's another design alternative for this rib. Okay, so that's it. And actually, it's all from my side for today. So, Chris, you can hand over the presenter.
Okay, thank you for that, Thomas. Just to wrap up, thank you all for attending the webinar session. I hope you found it interesting and insightful. Just as a reminder, we have the introduction to SCIA Engineer Part 2 this afternoon at 1:30. That'll be on steel structures. If you do have any further questions, please feel free to contact us through the details shown on the slide. If you're a customer, technical question, then obviously you can direct that through support. For anything else, please just email it through to myself, and I will ensure it gets forwarded on to the correct person. Yeah, and that's about it. We'll just stick around for a little bit just to try and answer the questions that are outstanding. If anyone's got any other questions, do just submit them now, and yeah, we will be back in touch as soon as possible. Wish you all a pleasant rest of the day. Thanks very much.
Thank you also from my side.